So yeah, in our last video, we ran our numbers into binary and looked for some patterns. And immediately we found a neat fact to confirm our previous discovery about powers of 2. And then we found these 3 classes of numbers, right? Powers of 2, all the other even numbers, and then all the odd numbers. And so we saw it was pretty obvious why powers of 2 always reduce to 1 under the Collatz conjecture. We showed why it's pretty obvious that all other types of even numbers become odd numbers. And then we had no clue where to go from here, right? And we've got infinite odd numbers. So even though we've split our problem, into these 3 classes and shown that one class is equivalent to another, the general problem of infinity that I was trying to reduce early on still exists. It's still hanging around. But, I'm an engineer, and mathematicians don't teach us all of their tricks. They just teach us how to calculate. So I figured, I would press on and calculate a bit. And I would see, well, maybe there's a class of numbers like powers of 2 that are odd. And maybe it's not all odd numbers, but maybe there's one type of odd number that will reduce to 1 every single time under the conjecture. So I monkeyed around, and I'm just sort of going to show what I found, right? But there is a class of numbers that always reduces to 1 under the conjecture, a class of odd numbers. And so that class of odd numbers is the series of binary numbers that have, this very interesting pattern, which is, if they just keep repeating this alternating sequence of 1s and 0s internally within themselves, these numbers will always reduce to 1. And the first example of this number is 5, right? And we saw earlier in our initial example, if you look here, you start at 5 turns into 16, which is a power of 2. And because 16 is the power of 2, it reduces to 1. So what this is here, what these binary numbers are examples of, are examples of odd numbers that when you multiply by 3 and add 1, we pick n so that 3n plus 1 is equal to some power of 2, right? So 5 we saw turned into 16, and the others are other examples, right? Like this one is 21, right? Because here, if we go 21 times 3 is equal to 63, and then 63 plus 1 is equal to 64, which is a power of 2. So yeah, we've got this fancy class of numbers that behaves this way. So the way I saw this, and it was really neat, was I was doing a lot of binary multiplication and addition by hand. And one thing you notice in binary, if you're doing a bunch of it by hand, is that doubling a number, so take 5, which in binary is 101, right? Well, 10 is 1010, right? So all we do to double a number is we shift it left and we add a 0 to it. So 5 is half of 10. And so 10 has this one additional 0 there. And we can note that 3n is equal to 2n plus n. So, right, like if I'm going to triple a number, that's the same as doubling a number and adding that number to itself. So if we take 5 and 10, right, if we go, we do it the old grade school way you learn to add numbers, right? This is 5, and this is 2 times 5. Well, binary addition works the same way decimal addition works when you stack the numbers on top of one another. So you get this lovely sequence of all ones, right? Which here is 15 in decimal. And then we know 15 plus 1 is 16, right? And pretty trivial. So if I'm going to add a 1 to this and complete this Collatz step, this 1 plus 1 is going to be 0, and I'm going to carry the 1. That's going to be 0, and then I'm going to carry the 1. And that's going to be 0, and then I'm going to carry the 1. And I'm going to get 1, 0, 0, 0, right? So this is 16 here. So there's, the way I think about it is there's this lovely thing where the numbers squish together, and then you add a 1, and it flips over every single 1 to a 0, and then that's a power of 2, which reduces to 1. So again, we've still got infinity odd numbers that don't match this pattern, but we have found a class of odd numbers that always reduces to 1. So we got some interesting stuff going on here. We found this nice little pattern. It pops out of this lovely little example of binary arithmetic. And it should be pretty easy to see why any number that's of this alternating 1, 0, 1, 0, 1, 0, 1 becomes, 1 under the Collatz conjecture.